With regards to the wave-like nature of an electron or the dual nature of electron, there are basically four parameters that are part of the quantum mechanical model and that help us define the uh, position of an electron within the electronic structure. So quantum numbers, they describe the characteristics of electrons and their orbitals. You already know that. Obviously, most of the information that you'll be gathering up today within this portion of the lecture, this is something that you already know from your high school physics. So the principal quantum number n, there are four parameters: the angular momentum quantum number, which is defined by L, the magnetic quantum number divided by M1, and the spin quantum number, which is defined by Mg. And the principal quantum number n, it basically describes the average distance of the orbital from the nucleus. So how far is your orbital from the nucleus? The principal quantum number n defines that. And you can define this principal quantum number with integers such as 1, 2, 3, 4, and so on and so forth. Uh, and the larger the value of the n, the higher the energy and the larger the orbital. Or in other words, the higher the value of n, the farther the orbital from the nucleus, having the higher energy. And chemists also sometimes refer to these orbitals as electron shells, but this one the same thing. Now, the angular momentum quantum number. This is basically defined by the letter L, and it describes the shape of the orbital. And the shape is limited by the principal quantum number n. That means for a specific n, you can only have limited number of shapes available to you, or limited number of orbit or suborbital shapes available to you. For example, or in other words, the angular momentum quantum number L, it can have shapes that could range from positive integer values. Uh, from it could have positive integer values, and the shapes would be restricted from 0 to n minus 1. So 0 would represent a shape. Similarly, n minus 1 would also represent a shape, and in between all the numbers would represent a specific shape. Uh, so it's basically a digit which is essentially representing the shape of your orbital. For example, if you have n value as 3, the three values that are allowed, or the three shapes of orbitals that are allowed, would be 0, 1, and 2. That means 0 to n minus 1 shapes are allowed for this third orbital. That means these three shapes, will come to know of these shapes, could be part of your third largest orbital. Orbitals that have same value of n but different values of L are called subshells. That means 0, 1, 2 for this orbital would be the subshells for this orbital number 3. The following letters correspond to different values. For example, letter designation for subshells: 0 represent the shape which is spherical or S. 1 represents the suborbital which is P. 2 represents the suborbital which is D, and 3 represents the suborbital which is F. So if I say that I have principal quantum number as 1, n is equals to 1, the only shape or the only suborbital I can have is n minus 1, which is 0. So I can only have one subshell in this uh, principal quantum number in this orbital. So the subshell that would be part of first orbital would only be the letter S. Ghulam Mustafa, kindly stop sending me the messages on the chat section. Uh, the second orbital, which is the orbital number 2, it would have uh, two subshells associated with it. the subshell represented by 0, which is S, and a subshell which would be represented by n minus 1, which is 1, and it can be designated with the letter P. I hope it is clear so far. Is there any confusion so far?
No, sir.
No, sir.
All right.
No.
All right. So the value of L defines the shape of the orbital, and the value of N defines the size of your orbital. Then comes the magnetic quantum number. Magnetic quantum number uh, is simply the number that describes how the various orbitals are oriented in space. Uh, or in simple words, how the subshells are oriented in space. And they again are dependent upon the value of n. The value of this number depends on the value of n. The values allowed are integers from minus L 0 to plus L. So for any subshell, you would have its orientation dependent upon the value of L. For example, if your L value is 0, you can only have one orientation. If your L value is 1, you can have three orientations: minus 1, 0, and 1. Similarly, if you have the L value is 2, you can have minus 2, 1, minus 1, 0, 1, and 2. These five orientations available with you, so on and so forth. So for example, if the value of L is 1, which is p orbital, you can write these three values for this number: minus 1, 0, and plus 1. So there are three orientations available to you, and this means the three different p subshells for a particular orbital. That means that the p shell would have same subshell would have same energy, but the orientation would be different. So P is a dumbbell shaped subshell. One of the shell is oriented across along the y-axis. One of the subshell is oriented along the x-axis, and one of the subshell is oriented along the z-axis. So you have three orientations available with you for the P subshell. Similarly, if we talk about S subshell, S would have the letter value or the numeric value of 0. That means it would have only one orientation available to it, and it would be having its center at the XYZ, and all the three orientation would be the same for the S subshell. S is a spheric subshell. Coming on to the spin quantum number, it says that the number describes the direction the electron is spinning in a magnetic field, either clockwise or counterclockwise. And within any subshell, you could only have two electrons having a spin of plus half or minus half, or clockwise or anti-clockwise spinning direction. So based on this, if we have to identify the electronic configuration, for instance, I have the electron which is the element which is represented as sodium, having 11 electrons. I start with the uh, shell having the lowest energy, which is 1s. How do I start filling up the shells? It is the sequence is uh, I hope you are familiar with this setup.
Yes, sir.
Where you can you help me? How do you write them?
सर आपकी आवाज नहीं समझ आ रही सर.
सर
बेटा
FDPS.
जब आपसे सवाल पूछा जाता है तब आवाज समझ नहीं आ रही होती. रेस्ट ऑफ द टाइम आर यू स्लीपिंग?
नो सर सर सही बोल रहा हूँ मैं.
तो बेटा लेट मी नो इन टाइम. मेरा आपकी आवाज समझ नहीं आ रही. जी बेटा.
सर इसको अगर फिल करेंगे तो सर इस तरह करेंगे. पहले सर वो जैसे हमने पढ़ा था भाई, स्कूल पब्लिक स्कूल डिविजनल पब्लिक स्कूल और फिर फेडरल डिविजनल पब्लिक स्कूल, सर इस तरह का.
All right, great. So you know that this would 1s, since one would have only the first orbital would only have the uh, s subshell. Then you'll have 2s and 2p, then 3s,
3s,
g, आगे
3p, 3p,
3p, 4s,
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 3d,
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 4p,
4P,
4
4P,
4p,
sir,
sorry,
4P आएगा
5s,
5s,
4d,
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 5,
5p,
6,
5P,
5,
5p, 6s,
6S.
6x,
all right. So you'll have this sort of electronic configuration available to you. In this case, you have for sodium 1s2 electron, 2s2 electron, 2p 6 electron, and 3s 1 electron. So you know the electronic configuration for sodium. Obviously, these six subshells would have the same energy for 2p, although they'll have their orientation different, but again, the energy level would be the same. So if I ask you for krypton having the atomic number of 36, can you write down its electronic configuration?
yes sir,
Yes, sir.
Yes, sir.
All right.
Yes, sir.
Yes, sir.
2.
All right. If you could write it down, that's good enough. I'll not ask you to write it down for me. I'll show you. For Krypton, this is the electronic configuration. Please do verify with it. The important thing is that the valence electrons are those that are occupied in the outermost shell. You already know that. Some atoms which are termed as stable or having stable electronic configurations, they are the atoms in which the outermost or the valence electron shells are completely filled. Moving on, uh, moving on towards the periodic table. Although
सर
you are familiar, Gigi,
सर वो पिछली स्लाइड में सर वो स्पिन
सर
और
CD और
स्पिन
4S
था।
शक्ल होती है वो बता दें।
1 मिनट जी, एक एक करके सवाल करें जी।
सर वो
सर मैंने
पिछली
कहा
स्लाइड
इसमें वो होती है ना शक्लिंग ES और सर 3D और 4S की सर वो उसका बता दें थोड़ा सा।
सॉरी, एक एक करके यार जी। स्पिन का कौन सा पूछ
उस्मान
रहे थे?
आप
स्पिन
पूछ
का
लो यार मैं बाद में।
सर मैं बोल रहा था स्पिन क्वांटम नंबर का एक बार थोड़ा सा दोबारा कॉन्सेप्ट बता दीजिए।
spin quantum number is basically how the electron is spinning in a magnetic field. It could either be spinning in a clockwise direction or anti-clockwise direction. So it just for simplified case, you need to understand that within any subshell, you can have only two electrons at maximum that could be present, having opposite spins. This is it about the spin quantum number. All right?
ओके यस सर।
जी, अगला सवाल क्या था?
सर मैंने ये पूछना था कि जब हमारे पास 26 होता है मतलब एटॉमिक नंबर हो गया तो वो हमारे पास सर वो S और D में सर वो होता है थोड़ा सा कंफ्यूजन सा आता है सर।
वो दोनों एक एनर्जी लेवल पे आ जाते हैं।
यस सर तो वो सर थोड़ा सा बता दें।
Don't worry about it. Just the bottom point. You don't need to get into the electronic. I'll not ask you to start writing the electronic configuration. Just you need to understand the point over here is that the electronic configuration, because I had already mentioned, if you remember, when we were talking to with regards to structure, the structure that you would be interested in would be the structure at atomic level. That means how the atoms are arranged with respect to one another in an in a material that basically would define your crystal structure. The subatomic structure, it is important from the concept of material science, but it is not important when you're talking about the materials from mechanical engineer's point of view. That is probably the domain of physicists or material scientists that are dealing in the domain of device fabrication or electronic devices. They are interested in electronic structures, how the energy levels are jumping, what happens when, since you are looking at this electronic distribution for a single atom. But in a material, when the atoms start to come together, how do the bands overlap? What is the valence band? What is the conduction band? What is the difference between these two bands? What is the bandwidth? So again, this portion of uh, electronic configuration, I guess this is sufficient for you to understand how the electrons are distributed in a continuous energy level bands. But beyond that, I will not take you into that, because that is not the scope of work in which mechanical engineers usually get involved. All right.
Yes, sir.
So you're getting the point. You will be interested
Yes,
more of
sir.
interested in the atomic level structure, not the subatomic level structure. So you don't need to worry about how do you differentiate when D and S shells they have the equivalent energy levels. You don't need to worry about that. Moving on into the periodic table, just having a basic understanding of periodic table, how the elements are distributed within the periodic table, increasing atomic number in several horizontal rows, which are called periods. You already know that columns have similar valence electron, and this means that they have similar chemical and physical properties. Uh, Inert gas filled electron shells that are stable electron configurations. That is the last of the columns that you have. Then the group 6A and 7A, they are the ones which are deficient in 1 and 2 electrons from stable electronic configurations. So 6 and 7, they are short of 1 and 2 electrons. Similarly, group 1A and 1,2, they are excess of 1 and 2 electrons. You already know that. 3, 4, and 5A, they display the characteristics of both metals and non-metals by the virtue of their valence electrons. And the group 3B to 2B, this is region which are known as transition metals, and they have partially filled d electronic states. Uh, from the point of view of bonding, you need to understand the elements which are situated on the right hand side of the table. They are more electronegative. That is, they can accept the electrons readily to form negatively charged ions. And the electronegativity increases from left to right and from bottom to top, as atoms are more likely to accept electrons if the outer shells are almost full, or if they are less shielded from the nucleus. I hope this point is clear to you. There's nothing new into it. All right.
Yes, sir.
All right. Great. So, all right. Before we take the break, we'll discuss this topic, which is uh, somewhat important topic about how the bonds are formed and how is the energy distribution as a bond is being formed. So, if you look at the if you have two atoms that are being brought closer together, there is basically the attractive force that exists between the two atoms. Uh, so as the two atoms are being brought together, the attractive force starts to increase. But at the same time, when they come in close contact with each other, such that there is electronic cloud present for both the atoms, and the electronic clouds start to come in contact with each other, there's a repulsive force that starts to dominate or starts to act. This means at a certain distance, the attractive force, the amount of attractive force and the repulsive force, they would balance out each other, and you'll have net force as 0. So this red line is basically representing the net curve that you are going to get as a result of this attractive force and the repulsive force. The net force Fn would be equivalent to 0 when the atoms are at a certain distance r0 from each other. So attractive force, particular type of bonding between two atoms, it is dependent on the particular type of bonding between the two atoms. Repulsive force, it is the interaction between the electron clouds of two atoms. small values of r, the outer electron shells of the two atoms begins to overlap, and when Fa, the attractive force, and the repulsive force, it becomes equal, then there is no net force acting on the system and a state of equilibrium exists. At this state, the centers of the two atoms will remain separated by an equilibrium spacing which is known as R naught, or it is also known as the bond length, uh, the distance at which the bond is formed between these two atoms. Now, is it clear so far? Are there any questions regarding to this bond formation?
No, sir.
No, sir.
All right, great.
सर आप इक्विलिब्रियम पॉइंट दोबारा एक रिपीट कर सकते हैं
जी,
जहाँ पे दोनों इक्वल होते हैं आप ऐसी कुछ बात करें
जहां पे आपकी अट्रैक्टिव और रिवर्सिव फोर्स बैलेंस आउट हो जाएंगी और
तो
नेट
ग्राफ
फोर्स
पे
जीरो हो जाएगी. सॉरी,
सर ग्राफ पे वो पॉइंट कहाँ से आएगा ग्राफ पे
अच्छा एक मिनट. ग्राफ पे वो पॉइंट यहाँ पे ये रेड लाइन जो आ रही है ना, ये ब्लू इज अट्रैक्टिव फोर्स, green is repulsive force. This red line is the net force that is acting on the system. At this point, the net force is essentially zero. So this is this this x-axis is showing the distance between the two atoms. So R naught at this point where your force is zero is essentially the equilibrium spacing. Clear enough?
सर उसके बाद वो सीधे रिपल्जन की तरफ
यस सर गॉट इट
जी सॉरी.
सर व्हाई इज इट हेडिंग टू रिपल्जन आफ्टरवर्ड्स
जैसे जैसे आप उसको इंटरएटॉमिक स्पेसिंग से करीब लाते जाएंगे, इलेक्ट्रॉन क्लाउड ज्यादा ओवरलैप करेंगे और ज्यादा रिपल्शन होगी.
ओके सर गॉट इट.
Right. Now, moving on towards the energy curve. Energy curve is a little different to understand. It says that as you are bringing the atoms together, the interatomic distance is decreasing, your repulsive energy starts to increase. And as the atoms are at a distance, at a much wider distance, there is attractive energy that is associated with the two atoms. Now, at this R naught distance, or the distance at which the bond is being formed, the difference between the repulsive and attractive force energies would be minimum. That means you would have the lowest point in the energy curve. This red curve, or I'll change my color in this purple one. All right. So this net energy curve, this would have a minimum point at this location where you have the bond length that is being formed. That is basically the equilibrium position or stable position having minimum potential energy. The bonds would have the minimum potential energy at this R naught distance. That means they would have the minimum potential to do anything except for forming the bond at this distance R naught. So this E naught energy from 0 to this point, it corresponds to the bonding energy for these two atoms. If you have to break up this energy, if you have to overcome this energy, if you have to break the bond, you'll have to provide this much amount of energy in order to break the bond. Is this point clear to you?
सर एक दफा रिपीट कीजिएगा जो आपने लास्ट पॉइंट सारा बताया.
लास्ट पॉइंट सारा बताया है, आप पूछे ना सवाल.
सर ये आप सर आपने बताया कि यहाँ पे पोटेंशियल एनर्जी वीक होगी लेकिन बॉन्ड फॉर्मिंग के लिए इनफ होगी.
नहीं, मैंने ये कहा है कि at this point, if you look at the net energy curve, this is the point having the minimum potential energy. That means at this point your bonds would be very happily existing together. All right, they would have minimum resistance to their bond. But if you have to break the bond, you would have to supply this much amount of energy, E naught amount of energy, in order to overcome the bond. Clear enough?
ये यानी कि बॉन्ड पहले का फॉर्म हो चुका होगा, उसे ब्रेक करने के लिए हमें ई नॉट एनर्जी चाहिए होगी।
जी बिल्कुल ऐसा ही है। आप ये भी तो कह सकते थे ना, एक मिनट, नेट एनर्जी कर्व यहाँ पे भी बॉन्ड बन सकता था, यहाँ पे नहीं बना। द बॉन्ड टू एटम्स वुड ट्राई टू गेट टू द मिनिमम पोटेंशियल स्टेबल पोटेंशियल, इस पोजीशन पे आने की कोशिश करेंगे, क्योंकि यहाँ पे वो सबसे ज्यादा महफूज समझेंगे अपने आप को। क्योंकि अब
But sir,
अगर
at that point, shall we?
जी यहाँ से उनको बॉन्ड्स को तोड़ने के लिए आपको इतनी एनर्जी कम से कम देनी पड़ेगी ताकि वो बॉन्ड टूट सके। तो यहाँ पे वो अपने आप को महफूज करेंगे, महसूस करेंगे। अगर मैं यहाँ पे कहूँ कि बॉन्ड बन जाएगा तो उनको बेसिकली इतनी सी एनर्जी चाहिए अपने आप को बॉन्ड को तोड़वाने के लिए या बॉन्ड को तोड़ने के लिए। तो दिस इज द मोस्ट स्टेबल पोजिशन दैट दे वुड लाइक टू बी इन, and E naught is the corresponding energy that you would have to supply in order to get them out of their comfort zone, which is the minimum potential energy position. Clear enough?
यस सर, क्लियर है।
Sir, minimum सबसे ज़्यादा स्टेबल क्यों, क्योंकि उसको तो आप ज़्यादा आसानी से तोड़ सकते हो, तो shouldn't they be considered as unstable at minimum potential energy?
आप ज़्यादा आसानी से तोड़ सकते हैं अगर आप मुझे देख के बताएं कि मिनिमम पोटेंशियल एनर्जी यहाँ पे है, यहाँ पे मुझे ज़्यादा एनर्जी देनी पड़ेगी तोड़ने के लिए, यहाँ पे ज़्यादा एनर्जी देनी पड़ेगी तोड़ने के लिए।
यस सर। सर इसका जवाब है इस तरह कि अगर ये होता तो फिर तो वो जो है नोबल गैसेस वो तो सर वैसे ही टूट जाती बहुत आसानी से।
नहीं, मैं अब आपसे तो मैं फिलहाल इस कर्व की बात कर रहा हूँ, नोबल गैसेस की बात थोड़ी कर रहा हूँ। मैं ये कह रहा हूँ कि यहाँ पे अगर मेरे एटम्स इस जगह पे पड़े हुए हैं या मेरे एटम्स जो हैं वो इस पोजीशन पे पड़े हुए हैं, कहाँ पे मुझे उनको तोड़ने के लिए ज़्यादा एनर्जी चाहिए होगी?
सर नीचे
सर
At the
फर्स्ट
first,
पॉइंट पे,
क्या पड़े हुए हैं उनके लिए ज्यादा
ए
चाहिए।
और
ऊपर
बी
वाले
में
एरिया
से
में सर ए पॉइंट,
ए
ए
पॉइंट
पॉइंट
पे
पे
ज़्यादा
जाता।
एनर्जी चाहिए होगी।
बी पे ही
जी
सर, ए पे ज्यादा चाहिए होगी
सर ए पे
एनर्जी।
ज्यादा चाहिए होगी।
सिंपल इनफ जवाब है कि जहाँ पे ज़्यादा एनर्जी चाहिए होगी तोड़ने के लिए वहाँ पे मैं सबसे ज़्यादा महफूज महसूस करूंगा, या वहाँ पे वो बॉन्ड्स जो है सबसे ज़्यादा स्टेबल पोजीशन में होंगे।
यस सर, ए ही चाहिए, ए होगा।
ऑलराइट, दिस वन थिंग। सो it further points out to three different things. Large bonding energies typically also have high melting point. जितनी ज़्यादा बॉन्डिंग एनर्जी ज़्यादा होगी, जितना ये डिस्टेंस फ्रॉम द जीरो टू नीचे होगा, उतना आपका मेल्टिंग टेम्परेचर हाई होगा। यानी कि बॉन्ड्स को तोड़ने के लिए और या मेल्ट करने के लिए आपको ज़्यादा एनर्जी रिक्वायर्ड होगी। क्लियर?
यस सर, क्लियर।
Yes, sir.
Then it says slope for stiff material at R naught position would be quite steep. Let's see how. If I look at this curve over here, सिर्फ मैं इस पॉइंट को कंसिडर कर रहा हूँ. So I have a curve of force versus distance, and I am referring to this point at which my net force is 0. अगर मेरी स्लोप इस तरह है या अगर मेरी स्लोप इस तरह है, दिस इज केस 1, दिस इज केस 2, तो मुझे एक जितनी फोर्स लगा के किस पे ज्यादा सेपरेशन क्रिएट कर सकता हूं मैं? इफ आई अप्लाई फोर्स F1, in which case I would have more distance created between the atoms.
sir, at D2.
D2, or in the case where my slow, or in which case I would have to apply, or in which case the force F1 would create lesser separation.
At case 1.
Case 1. That means if my slope at R equals to 0, This is r equals to 0. If the slope at r equals to 0 is higher or steeper, that means my material would be more stiff. Is this clear to you?
No,
ये
sir.
point
Stiff part clear.
जी
Sir,
ये
stiff
point
part.
नहीं सर, ये बात क्लियर नहीं हुई सर।
नहीं क्लियर हुई। अच्छा देखें, स्टिफ से मुराद ये है कि आई अप्लाई अ फोर्स, तो स्टिफ मटेरियल वो होगा जो कि इस फोर्स पे the amount of force that I have applied, it would give me lesser separation, जिसकी d वैल्यू या एटम्स की सेपरेशन वैल्यू कम होगी। क्लियर? ज्यादा ये पॉइंट
Yes, sir.
समझ में आया?
यस सर, यस
ये,
सर।
ये दो एटम्स हैं, इनके ऊपर मैं फोर्स F लगा रहा हूँ, तो स्टिफ मटेरियल वो होगा जो कि कम डिस्टेंस ट्रेवल करेगा फॉर द फोर्स दैट आई हैव अप्लाइड। क्लियर?
Yes, sir.
यस यस सर, क्लियर।
अगर मैं कहूँ 1 और 2 में मैं फोर्स F1 लगा रहा हूँ, तो स्टिफर मटेरियल कौन सा है?
Sir, first material.
फर्स्ट
दिस
सर
इज
First
स्टिफर
material.
मटेरियल, बिकॉज उतनी ही फोर्स पे ये कम डिस्टेंस मूव कर रहा है और दूसरा जो है वो ज्यादा डिस्टेंस मूव कर रहा है। सो इन दैट केस माय मटेरियल व्हिच इज हैविंग higher slope or steep slope, one is having steep slope as compared to 2 at this point. Is it clear?
Yes, sir.
So
यस
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 सर, क्लियर है।
So a material that is having a steeper slope at at this r equals to the bond length, you would have a stiffer material. Clear enough?
Yes,
Yes, sir.
यस सर, क्लियर।
Yes, sir.
दूसरे लफ्जों में, let me try to make you understand in a different way कि let's say I have this. So एक मेरे पास कर्व ये है जिसकी स्लोप इस तरह कुछ है, एक और मेरे पास कर्व है जो ऐसे आ रही है जिसकी स्लोप ऐसे है। तो इन दिस केस एक ये स्लोप है, एक ये स्लोप है। कौन सा मटेरियल मटेरियल 1 और 2 वुड बी मोर स्टिफ?
सर 1।
sir, material 1.
जी
जिसकी स्लोप
1
ज्यादा
वुड, जी 1 would be more stiff.
material
So
one.
जी very good. So at the position r equals to r naught, the curve with having a high slope would be more stiff. The third thing is, for the energy versus r curve, the deep and narrow trough, that means the more depth and the more narrower your curve is, you would have a lower coefficient of thermal expansion. Clear enough? All right.
यस सर।
यस सर।
All right. So we'll have a break of 10 minutes at this point and we'll come back and start with the session. All right.